Welcome. Today we are going to talk about something called QN, quantifier negation rule. Well, in fact, it's not a new rule. You have seen this a few weeks ago, and today we're just gonna formally restate it as a rule. Before we talk about this new QN rule, let's do a quick review of all the rules that we've been discussing so far. Different rules have different requirements for what you can infer from what. So always be mindful of them. So first, there is EG rule, existential generalization. And under this rule, you may infer an existential sentence from its instance. Next, there is UI, universal instantiation. And in this rule, you may infer any instance from the universal sentence. Then there is EI, existential instantiation. So from an existentially quantified sentence, you may infer its instance with an existential name, that is lowercase e, and E1 and E2 and so on. So every time we use EI, we should introduce a brand new existential name. And there's UD, universal derivation. The rule says you may infer a universally quantified sentence from its instance if you follow some specific procedure, and we'll come back to this. So here's a simple example. EI first on line number 1. So from line number 1, I infer FE, and the rule is EI. And from line number 2, and line number 2 is a universal statement, so you know that you can infer any instance. That means I can infer this, line number 2, using UI. And number 3 and 4, that's MP, modus ponens setup. So I can get GE from 3 and 4 modus ponens. And from line number 5, I can use EG, existential generalization, and get sum x gx. Now the proof is completed. So this is very simple proof. And here's one very important lesson. That is, when there are simultaneous opportunities for UI and EI, we have to do EI first. So here in this proof, we used EI first in line number 3, and then we used UI. And let's see what happens if we used UI before EI. Suppose I do UI first. So I get UI from line number 2. And here, note this. From line number 1, I can do existential instantiation, of course, using existential name, but there's a restriction. We have to use a brand new existential name, and in line number 3, lowercase e appears already. Therefore, when I use EI on line number 1, I have to introduce a brand new existential name, which is this. Note that number 3 and 4 do not create an opportunity for MP. So what I need to do is to use UI again on line number 2, and this time I should get this, and then I'll be able to do MP, do EG. So you want to use EI first so that you can take care of all these restrictions first, and then later you can use UI without having to worry about any restriction whatsoever. So now let's talk about UD a little bit more. So UD says you may infer a universal sentence from its instance if you follow some special procedure. And the procedure is this. First, you have to indent beginner scope line and declare a variable for universalization, which has never appeared as free in any previous line. And then you close this subproof by deriving an instance of the target sentence. And this derived instance has to be made up of the variable that you have declared in step 1. So here's an example, and you saw this example already, so let me be quick. So we want to use UD, so that means we need to open up our subproof. So indent, scope line, and declare a variable, and let me just choose U. And your task in this subproof is somehow you prove an instance of the target sentence, the highlighted sentence. So you want to prove an instance of this target which is made up of this variable that you have declared. That means at the end of this subproof, you want to prove this. Line number 1 is universal sentence. So getting an instance from line number 1, I can get this. We can transform line number 3 to this. And since line number 4 is conjunction, we can do simplification like this and this. And from line number 6, then we can directly infer GU arrow HU using arrow plus rule. And your subproof is completed. Line 7, it's an instance of the conclusion, and it is made up of the variable that you have declared in line 2. So your job is done. Now you are entitled, you are licensed to assert the conclusion itself, and the justification will be universal derivation. Now let's talk about QN, quantifier negation rules. And in fact, you saw this a few weeks ago when we discussed negations of categorical sentences. To refresh your memory, here we go. The first one says it's false that everything is an F. Then it's same as saying there is something that's not an F. And the second one says it's false that something is an F. That is same as saying nothing is an F, and so on. So we saw that all these mean the same thing. The left-hand column means the same thing as the right-hand column here. Now we're going to have syntactic rules that reflect what we just saw, the QN rule. So the rule says when you have a negation of quantified sentence on the left-hand side, like this, and like this, then you can turn them into the sentences on the right-hand side like this and like this. And the most useful QN rules are the first two versions, from left to right. And here's a very important rule of thumb. So when you have a negation of quantified sentence in the premise or assumption you made for CP or IP, apply QN rule to them first. Okay, let's do an example. Pause the video, take pen and paper, and try it for yourself before moving on. Okay, so probably what we want to do first is to open up our UD, universal derivation, because the conclusion is a universal sentence. So in line number 3, I indent and I declare a variable. And from now on, for the justification, you may leave it empty because in our class, the only case you have a single variable in an indented line like this is when you open up your UD. So when we see an indented line with a variable, by now we know that it's just a variable declaration steps. From now on, you don't need to write out variable declaration. You just indent, scope line, and write down a variable, and we all know it's a variable declaration step. Now, in this subproof, our task is to prove FU arrow HU. Somehow, at the end of this subproof, we want to prove FU arrow HU. Well, it's an instance of our conclusion, and it's made up of the variable we just declared. So then the question is how to prove FU arrow HU, and there are many different ways. You can use IP if you want. And here, I'm just going to use CP. That means I have to open another subproof for CP. So I assume FU, and this is assumption for HU. Line number 1 is a universal sentence, so you know that you can infer any instance from line number 1. And in this case, obviously, having this instance from line number 1 will definitely help you because you can use MP and get GU. What else can we do? And we haven't touched line number 2, so I think this is time to operate on line number 2. And this is perfect time to use our QN quantifier negation rule. Line number 2 is a negated sense, negation of existential quantifier. So according to QN rule, I get this. And note that QN rule transform line number 2 into something very useful, which is line number 7. Line number 7 is now universal sense, so you know that you can do universal instantiation. So I can get this. And line number 8 is a perfect opportunity for De Morgan's law. And note, line number 6 is GU. And if you get double negation on line number 6, then you'll get not GU, which is a negation of the first disjunct in line number 9. That means you will be able to use disjunctive syllogism. You saw this trick 100 times by now. And you can get using disjunctive syllogism. And we don't like double negations, so get rid of double negation and get HU itself. And note our job is done now. In line number 4, we assumed FU for CP, and that assumption was for HU. And in line number 12, we proved HU. So, and assert this thing. We see that in line number 13 is an instance of the conclusion that I want to prove, and it's made up of the variable I have declared in line number 3. So this means I have satisfied all the requirements for universal derivation rule, which in turn means that I'm now entitled to assert the conclusion itself. Step 3 through 13, universal derivation. Great. And here we just use CP, but I said IP is also possible, so I'll leave it as homework. Solve this proof using IP, not CP. Okay, now from now on, you may abbreviate some steps. For example, you may abbreviate UI step and NP step into a single step like this. And also, you may abbreviate UI and De Morgan's procedure into one single step like this. Personally, I don't really recommend abbreviation. Some answers in our textbook are using abbreviations like this. So I'm just showing you that abbreviation is just possible so that you can understand those answers in the textbook. If you want, you may, but you have to be very careful. Abbreviate only when you are absolutely sure and know what you are doing. If you abbreviate and make mistakes in doing so, it will hurt your grade. You've been warned. Now let's do a bit more challenging proof. As before, pause the video and try for yourself. Okay, first, note that line 1 is a conditional. It's just an arrow statement. It is not a quantified sentence. So you cannot use any of the quantifier rules like EI here because simply it does not apply. So then it means there seems nothing we can do. And recall, when there's nothing we can do, consider IP, indirect proof. So let's open up an IP, indent, scope line, and assume the opposite of what you want to prove. So in this case, it will be not sum x fx arrow gx. Now this is an opportunity for QN rule. Use quantifier negation rule, and we get this. Now what? There's nothing. But I see that I can do something about line number 3. Line number 3 is a universal sentence, so it means I can use UI. Which letter I need to use? I don't know, but I know I can infer some instance from line number 3. So let me use UI, and just let me use lowercase a this time. So that is, I'll get this. Then note that line number 4 is not arrow statement. So it means I can use not arrow row. Using not arrow row, I can get this. And then look, there's something we can do here. See, we have f of an a in line number 5. And from this particular statement, we can infer some x fx using easy row. And this is great because now we can use MP, which will give us some x g of x. From line number 5, I can get some x fx using eg. And number 7 happens to be the antecedent of line number 1, which means I can use MP, modus ponens. And as a result, I'll get this. Now what? From line number 8, we can infer something, right? At least we can infer an instance using lowercase e. So we can get GE in line 9, 8 EI. Now this is interesting. See, we are in the middle of indirect proof, IP. That means we somehow need to drive a contradiction. And is there any contradiction we can drive? Well, pause and think for yourself. This is very important. And note that line number 6 and 9, they are not really contradicting each other, but they are almost contradiction, right? Line number 6 is not GA, and line number 9 is GE. So if we could have GA, then GA and not GA will give us a desired contradiction. But we cannot get GA. See, line number 9, GE, was obtained through EI row, and EI row dictates that we use lowercase e, existential name. So it doesn't seem possible to get GA. Now back to our line 6 and 9. Is there any possibility that we can somehow get not GE? Because if we could, then we would get GE and not GE, and this will give us a desired contradiction. Can we? And yes, the answer is yes. Look, where does this not GA come from originally? Well, it comes from line number 4, line 4, and line 4 is from line number 3, which is a universal statement. And recall, again, from universal statement, we can infer any instance we want. So this means I can get not FE arrow GE from line 3 through universal instantiation. And then, using not arrow row, I can get not GE from line number 10. Then my job is completed. Line number 9 says GE, line number 11 says not GE, so I have just discovered a desired contradiction. So I can declare that I have found a contradiction which arises from line number 9 and 11. And by showing line 12, I have satisfied the requirement for indirect proof. So that means now I'm licensed and entitled to assert the thing itself. Note that the UI step in line 10, this step is necessary. This is because if we had used E for the UI in line number 4, then we would have had to use E1 for the second EI in line 9, hence we would still have to have used UI again in line number 10. So line number 10 is a necessary step. Yeah, I think this was very interesting proof. Okay, here's another proof I want to try, and I'll leave it as homework. This is it for today. Thank you, and I'll see you next week.